Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. And also known as the House of the Lowering Chair. Literally, if I just kind of get here, I'll sink a little bit every so often. I don't know, it just started my last video I recorded, and I don't really know what's going on. I'm just going to adjust myself right now, and we'll see how often this happens. Step on inside. Watch some Titanic is on. Watch some Titanic. This is the near the beginning stuff. Let's do a 7.1 to 7.3 review of the Big Ideas Math Integrated Math 2 textbook. We're on a chapter of quadrilaterals, and so far we've looked at things regarding angles of polygons, interior and exterior angles. We've done their sums, we've done them for regular polygons. Then we started looking at parallelograms. What makes something a parallelogram, and if you have a parallelogram, what you can do with that something. All about their properties. We've done some proofs. We've done a lot more of just the algebra things, maybe some things with graphs. We have a quiz for you in action here, a review for 7.1 to 7.3. Let's go over those. If you want to see what 7.1 to 7.3 look like, including 7.2, go ahead and check out the playlist in the description section down below here. If you'd like to check out what the 7.1, 7.3 quiz looks like, it's 22 questions, also a PDF straight down below, probably the first link there, and a timestamp for each problem. I'm going to go ahead and get started with you guys right here. Without further ado, let's check out what we have. We're going to begin with finding the value of x in numbers 1, 2, and 3. They show you in section 7.1 here. 7.1 is all about the angles of polygons. And what we have, I don't know what to do about this chair. What we have in this situation here, and it's one problem at a time, but I got a quadrilateral, 1, 2, 3, 4 sides, which also means 4 angles, and a 4-sided polygon, quadrilateral, like a parallelogram, has an interior angle sum of something. We'll figure out what that is right now by using this formula here. The degree sum of the interior angles is 180 times the number of sides you have minus 2. Now, we should know through the corollary, I believe they call it, the extended corollary, that a quadrilateral's interior angle sum is 360 degrees. With that said, these angles add to 360 degrees, including the x, which we want to find. X plus that 70 plus 95 plus 115 equals 360. Probably should be looking at my calculator here and there, but we'll see. That's 200. It's 280. Subtract 280, you get x equals 80 degrees. And I like to kind of double check just by looking at the diagram they have, and I can believe that that's 80 degrees. It looks a little less than 90, and it looks right to me. Because they are, despite what they say about things not being drawn to scale, they are probably made drawn to scale. We just aren't supposed to be measuring with a protractor. We're supposed to be solving algebraically. All right, number 2 is the same exact kind of problem, interior angle sum, but it's not a quadrilateral this time. It is a 1, 2, 3, 4, 5. Let's do that together. 1, 2, 3, 4, 5-sided shape. It is a pentagon. Just like that quadrilateral, it's not a regular pentagon. It's not like the look of the defense building. It is irregular. All angles are different. The sides are different. X is going to be something probably obtuse looking, but let's find the interior angle sum of a pentagon, which should be 180 more than that of a quadrilateral. 180 times n minus 2, n being the number of sides is 5, so 180 times 3. Now, I've spoken quite a bit in section 7.1 regarding how this interior angle sum formula comes to be, the 180 times n minus 2 bit. It has to do with the number of triangles in your drawing, in your polygon. But look to those videos for that. Look to 7.1 for that. Okay, so right here, we're going to add x with 60, 120, 150, and 75. This will add up to 540 degrees. 60 plus 120 is 180, plus 150 is 330, plus 75 is 405. X plus 405 is 540. Subtract 405 and you will get x equals 135 degrees. That's obtuse enough for me to be convinced that that is the correct answer. Number 3. This time we have x on the outside, and not just on the outside. This is what is known as an exterior angle. If you extend a side from a polygon, it is going to be a linear pair, forming a linear pair with one of your interior angles. It's not the whole exterior angle. This is an exterior angle. Again, supplementary with interior ones. We don't need to deal with the supplementary part right now. What we need to deal with is the fact that an exterior angle sum of any polygon, regardless of the number of sides, is always 360 degrees. So straight up with this problem, I'm going to already add these things up, and I already know what these things are going to be set equal to, given that they are all exterior angles. As I sync, these all add up to 360 degrees. 60 plus 30 is 90, 162, 208. Is that a 55? 263. Combining like terms. Subtract 263, and I'm getting, I guess, 97 degrees. Looks like a little bit more than 90 degrees, so I'm going to go with it. That's what I like, my gut instinct. That's numbers 1, 2, and 3, section 7.1. Also out of section 7.1, let's look at numbers 4, 5, and 6. Find the measure of each interior angle and each exterior angle of the indicated regular polygon. Now, a regular polygon has all congruent sides and angles, unlike those other ones right here, which were irregular. A regular decagon would look like this. I mean, literally, I'm able to make the shape with this tool here. So regular decagon, that is a 10-sided shape. It'll look like that. All sides congruent, all angles congruent. Now that part doesn't matter for us other than to understand that you're going to get obtuse angles here, and for the exterior angles, you're going to get pretty acute angles there because, of course, they are linear pairs. They're supplementary with those interior angles, right? So just something to keep in mind. Now, the first way that I'm going to do this problem is, to me, the longer way. I'm going to begin with the interior angle sum, and this is the way I'm going to do this problem, and maybe the second one as well. And third and fourth way problems, I'll show you something else in what I do. Let's start with the interior angle sum of a decagon. Let's take a look at what all these things would add up to. 180 times 10 minus 2. It's 180 times 8. 8 half rotations is 4 rotations. That is a 1440 spin in snowboarding. 1440 degrees. Now that's the sum. That means all of these, and I'm going to give them I, not for like imaginary number I, but like as a variable. All of these are the same angle measure. This is a regular decagon. How many of those are there? There are 10 of them. Now, you could set this up almost like an algebraic equation, 10i equals 1440, but we probably do a little bit more of just the interior angle sum is the degree, the measure of each interior angle is the interior angle sum divided by the number of sides / angles, like that. You'd go a little bit more that way. You get 144 degrees from that. So that is the interior, that is an interior angle measure. Now, the exterior angle measure, you have one of two options in what you can do. Remember, an exterior angle measure E, not to be confused with the natural constant E, just as a variable, each of these E's are linear pairs with your interior angle measures. If I want to find any of the E's here, I can do 180 minus 144 because they should be supplementary together, and that would be 36 degrees. Now, you have a second option for E. The second option is, because they're all the same, 10 of those E's would add up to 360 degrees. All exterior angle sums, no matter the polygon, is always 360. I'll do that for number 5 after I still do the degree thing for number 4, and then we'll talk about how we can do it even faster for 6 and 7. Number 5, a 15-sided polygon. It's not that there's not a name for it. I assume there is. I don't know what it is. Quintessagon. It's that if they told you it, they don't expect you to know. They expect you to know decagon, though. Anything up to 12, for some reason not counting 11, which I think is a hendecagon. All right, a 15gon. D is 180 times 15 minus 2, or 180 times 13, which I don't know. 180 times 12, though, is... I don't know that either. 216. Is this 228? 2280. I should probably something about that does not sound right at all. 180 times 13. 2340. I was off. 2340. Okay. So that's the sum. Once again, the I, we can take 2340 and divide by the number of sides or angles, 15. Let me use my calculator for that one. I divide by that 15. And I'm getting 156. So 156 degrees exactly is the measure of each interior angle of that polygon. Okay. An exterior angle measure, like I said, I could do the 180 minus 156, probably recommended, but I could also do 360 divided by 15, the number of sides that there are. And I should know 360 divided by 15. For some reason, I'm 24. 360 divided by 15. Yeah, 24. So 20. Oh, I should know it because the other one is 156, right? Those should be supplementary. So that's the second way you can do it based on that. Now, for numbers 6 and 7, I'm going to go even more quickly. If you guys agree that the exterior angle measure for these circumstances is significantly easier to find the interior than the interior angle measure because the sum is always 360 degrees. Straight up, if we could find the exterior angle measure first, do 360 divided by, this is a 24 gon, so we'll divide by 24. Well, 360 over 15 is 24, and 360 over 24 is 15, so that's one I know straight up. Why does this help me finding this one first more? Because they never asked for the interior angle sum. I'm finding it for one reason and one reason only. The measure of each interior angle. I divide the sum by the number of angles to get the measure of each angle. But if I don't need the sum and I have another way to find the interior angle measure, I'm going to do it, which is this. They make a linear pair. I equals 180 minus the exterior angle 15, 165 degrees for that guy. That's the quickest way you can do these problems. Now, I'm showing you all these different ways just so you're aware of them, and you might be asked to find the sum. And you can find the sum by multiplying that number by 15. But at that point, you're kind of swimming in circles. Now, you might notice on all these problems here, and it's probably better if I actually write down what these things were, like decagon, 15 gon, 24 gon, and 60 gon. 15 gon, 24 gon, and 60 gon. What you might notice is these are all increasing in size, at least number of sides size. And I'm going to do exterior angle again first, which if you're noticing the exterior angle measures are getting smaller and the interior angle measures are getting larger. How large? They start to approach 180 degrees. Clearly they cannot be convex, but they also can't even be 180. Otherwise, it's just a straight line throughout. But they start to get a lot more circular. And I can't do a 60 gon with my tools right here. The best I can do is 16. Check out what a 16-sided shape looks like right there. That's getting pretty circular in nature. Compare that to a circle, literally. I mean, that's just a 16-sided shape. Now, of course, you can see the sides, you know, the angles, stuff like that. That's 16 sides. Imagine 60. Getting pretty circular in nature. Anyway, 16. Did we have 16? No, we had 15. 15 is 156 degrees. That's pretty close to that thing right there. All right, I'm going to move forward. Getting a little chatty. Numbers 8 through 15. Oh, that covers a lot of problems pretty fast here, all with one diagram. Let's go ahead and take that diagram. This is section 7.2. We're moving on to the parallelogram stuff. 7.3 also has parallelograms. This is more parallelogram definition and properties. 7.3 is more proving something is a parallelogram or using things if it were, what would you have? Which is a lot of questions like this. So number 8, or numbers 8 through 15, we're going to find the indicated measure in parallelogram ABCD, explain your reasoning. I'll probably explain more things as I go, but I'll start just by saying a parallelogram is a quadrilateral with opposite sides parallel. That's its definition. There are at least 4 properties along the way worth discussing, and it'll probably bring about within the stuff here. We'll talk about it when we get there. Such as, number 8, we need to find the length of segment CD, right here. Well, not only are opposite sides parallel in a parallelogram like this, which we might be able to use for some information later, but opposite sides are also congruent. AB and CD are the same length. CD is 16 because AB is 16. That's number 8. Number 9, let's find the length of AD. AD, I did mention opposite sides were congruent, so AD will be congruent to BC. That means they'll also share equal length. So the length of AD is the same as the length of BC, which is 7 units. Number 10, the length of AE. Looks like the first 4 are lengths and the last 4 are measures of angles. The length of AE. AE is part of a diagonal. The entire diagonal is AC. You know what AE is, though, also? It's half of the diagonal, because each diagonal in parallelogram, here's another property, they bisect each other. That means these two lengths are the same. If AE is 7, then so, excuse me, EC is 7, then so is AE. AE is the same as CE, which is also 7 there. Number 11, the length of BD. BD is the entire other diagonal. Now, what do we know about that diagonal? Nothing? Oh, 10.2. I was going to say. Okay, so I assume this is the 10.2 for DE. Now, BD is the entire thing. Like I said, diagonals bisect each other. So 10.2 will be half of that length. BD is the length of two BEs, DEs, I should say. Or two BEs, but we don't know that length. We could. Which is 2 times 10.2, which is 20.4. So that's the first 4 in that guy. Let me do this down here so I can fit some over there. I want to see the diagram still. 2 times 10.2, which is 20.4. Okay. All right, let's go to... One sec. My external hard drive is thumping against something as it's chugging along. All right, let's go to numbers 12 through 15 for the same diagram. Let's start talking about angles and how parallelograms have certain things with angles. I should probably do a boop and boop. Okay, number 12, measure of angle BCD. Where is BCD? BCD is right here. So measure of angle BCD, what is this guy? Well, opposite angles in a parallelogram are congruent. We know the measure of angle BAD, or DAB, however you want to put it, is 120 degrees. So is this. They have equal angle measure. They're both 120 degrees. Another property of parallelograms. Number 13, measure of angle ABC. ABC is the other angle type that you see here. Now we have no known measurement within there. We have a measurement here of 43 degrees, but unlike diagonals bisecting each other, they do not bisect the angles. I can't assume if this is 43, then so is this, and therefore this is that over there. But these angles opposite each other are congruent. I will say this 43 has nothing to do with what we're going to do. We're actually going to use the 120 to figure this out. Consecutive angles are supplementary to each other in a parallelogram. Now this is really due to the parallel lines. These parallel lines, such as these ones here, cut by this transversal, create a same side interior angle pair among those two. Right there. So, measure of angle ABC is 180 minus the measure of angle BAD. We already know that's 120. And 180 minus 120 is 60. So this is 60 degrees. So is the other one opposite, but I think that's something we might be using later. I don't know for sure. Number 14, measure of angle ADC. Yes, this is exactly what that is. So this is going to be either opposite that angle we just found, which will be congruent to it. That means we're going to get another 60-degree angle. Or you can say it's also forming a linear pair for the same exact reason with the other guys. Consecutive angles are supplementary. So ABC, also 60 degrees. And lastly, we still haven't used that 43 number. I assume it's about to be in effect. Measure of angle DBC. So DBC, let's take a look at where that is as we do this. Measure of angle DBC. DBC is this. DBC. It's this guy right here. And once again, parallel lines. This line is parallel to this line right here. But they're not just cut by the sides of the parallelogram. They're also cut by transversals, such as the diagonals. This diagonal here, two parallel lines cut by transversal. This guy relates to this guy over here, the 43-degree angle. You know how? They're alternate interior angles. This is not a property of a parallelogram. This is a property of parallel lines. Alternate interior angles are congruent. It's equal to the measure of angle, if I want to call it ADB. Is it DBC? I'll call it BDA. BDA, which is also 43 degrees. They're both equal in measure. And there's that. So I think we used every number on there. We used a lot of the properties involved with parallelograms. Opposite sides congruent, opposite angles congruent, consecutive angles supplementary, and diagonals bisect each other. And then we just use concepts of parallel lines to find other parts. And that's a lot of 7.2. Okay, section 7.3. It's more on parallelograms, and the kinds of questions that they ask can be different. State which theorem you can use to show that the quadrilateral is a parallelogram, number 16. So on number 16, there's a, I should know the names, but there are theorems to state, all right, is this enough information to say it's a parallelogram? What theorem is there? And a lot of our parallelogram proofs, a lot of our properties and theorems, obviously theorems are built on proofs, but the properties are built on proofs as well, congruent triangles and stuff. The one you're going to look at in number 16, you can notice you have one pair of opposite sides that are known are parallel. That's not true of parallelograms. You need both. I don't have both, but if you did know that that pair of opposite sides are also congruent, that would be enough information. Number 16 is a parallelogram by the opposite sides parallel and congruent theorem. I hope I'm not making that up. So they have names, and I'm not really good at those names. And I don't think many teachers would be too hurt if you didn't know them either. You need to know the reasoning, and that's the reasoning. A pair of opposite sides are parallel and congruent. The same pair. It will make a parallelogram. It's enough information. We can actually prove it. We have. These diagonals bisect each other. Now, the parallelogram has a property that states diagonals bisect each other. So we're flipping this thing on its head. If diagonals bisect each other, it's a parallelogram. This is a converse theorem. This is the parallelogram, diagonals converse. I believe I'm saying that right. Parallelogram, diagonals, converse. Or diagonals converse theorem. I really should look these up. Let's see if I have a way of doing that. I don't want to get these things wrong. Let's pop up my 7.3. You won't see this, but this is called the... Was this 7.3 that they were in? I can't find it. Parallelogram, diagonals, converse. That is the name of it. Okay. All right. Let's keep moving forward. Let's look at number 18. Now, number 18 has both sets of opposite angles congruent. We see the marking for these two to be congruent. We see these are both 63. Same measure means congruent. So number 18, this is also the parallelogram properties. The opposite angles are congruent, both pairs of them. If both pairs of opposite angles are congruent, then it's a parallelogram. That's also a converse. This is a parallelogram. Opposite angles converse. So that's a little bit of 7.3 for you. I'm sure we're going to have more coming up right now. Looks like I'll attach graph paper down below. Number 19. 4 more. Graph the quadrilateral with the given vertices in a coordinate plane. Then show that the quadrilateral is a parallelogram. So once again, we're still in section 7.3, showing that it's a parallelogram, right? That's the whole thing. Prove that it's a parallelogram within what you have. We have a bunch of different theorems that we just looked at right now that can prove any of them. Another converse theorem that we did not do is the opposite sides congruent one. Or we can go by parallelogram's definition. Both sets of opposite sides parallel. I probably wouldn't use the angles one because we don't really speak on angles so much with graph stuff. But if I have Q at -5, -2, R at 3, -2. Oh, this is going low. Hold on. Q, R at 3, -2. S at 1, -6. And T at -7, -6. I mean, doesn't it just look like a parallelogram? Wouldn't you agree that it just is, that you can just say, look at it and you're good? No, probably not. However, we can prove it. You have different methods, different options. I try and go for the easiest ones possible, and because we have 2 questions with them, I can kind of check out both of them for what they are. This one, I'd really like to play a lot with the horizontal lines because I know horizontal lines are parallel with each other. They have the same slope. That slope is 0. The slope of segment QR is 0. The slope of segment TS is 0. one of the conditions a parallelogram needs is opposite sides parallel. It needs both sets, and we could do both sets, but I want to go a little bit differently for this one. Let's also talk about QR and TS in terms of their length. 1, 2, 3, 4, 5, 6, 7, 8 is this length. And 1, 2, 3, 4, 5, 6, 7, 8 is this length. So they are congruent to each other. The length of QR is 8. The length of TS is 8. This is that theorem that would be used on problem number 16 as well. The opposite sides parallel and congruent theorem. If one pair of parallel sides, if one pair of sides are both parallel, opposite sides are parallel to each other and congruent to each other, then your quadrilateral is a parallelogram. So these two things, check that one out by the, again, opposite sides parallel and congruent theorem. I feel like I wrote exactly that once before. That's number 19. Let's go to number 20. Same concept. We'll maybe find a different method, different means. Shake it up a little bit. Nothing wrong with what we did. However, that helped because I had horizontal lines. It's easy to count horizontal lines that way. Does number 20 have horizontal lines? I have no idea. W is at negative 3, 7. X is at 3, 3. Y is at 1, negative 3. Does not look like anything's going to be horizontal here. Z is at negative 5, 1. Z is at the negative 5, 1. Okay. Another type of quadrilateral. We got to see how it's a parallelogram. Let's go just more with the parallelogram's definition. Definition is opposite sides parallel. Now, last time I mentioned these slopes were 0 because they're horizontal lines. That's almost as straight up as I can get. Or not straight up, literally the opposite of that. However, here we can dive into slope concept. If I find the slopes of opposite sides by the rise and run, how much do I rise and run here? How much do I rise and run here? Even same from how much do I go down and over? How much do I go down and over? All these slopes, if they have opposite slope things that are parallel for both sets, then you also have a parallelogram. This is rise of 1, 2, 3, 4, 5, 6, and run of 1, 2. Rise of 6 over 2. Same thing here. Rise of 1, 2, 3, 4, 5, 6, and over 1, 2. The slope of segment WZ is 6 over 2, which is 3. The slope, I think I gotta sneeze. Slope of segment XY is also 6 over 2, 3. That's one set of opposite sides that are parallel. I can either find their lengths, and listen, their lengths would be the same. They both have a rise of 6 and run of 2. The whole 6 squared plus 2 squared equals, I can use Pythagorean theorem for it, forget distance formula. But let's just go one step further. Let's look at ZY to WX. We go down 1, 2, 3, 4, over 1, 2, 3, 4, 5, 6. This is also down 1, 2, 3, 4, over 1, 2, 3, 4, 5, 6. So the slope of each of these, WX, is negative 4 over 6, which is negative 2/3. The slope of YZ, I like to go alphabetical, is negative 4 over 6, which is negative 2/3. All of these solidify two pairs of opposite sides parallel. This is the definition of a parallelogram. The very definition. That means this quadrilateral is a parallelogram. By definition. So I'm showing it that way. Okay. So again, you kind of have options on what you want to do. And those were mine. All right, 2 more questions. Section 7.1 kind of question. A stop sign is a regular polygon. This is the one I generally bring up for octagons, which is what this is. Classify the stop sign by its number of sides. Okay, I just gave it away. So on number 21, stop sign. Part A, this is an octagon. It's 8 sides. It's a regular octagon, I should say. Regular octagon. Part B, find the measure of each interior angle and each exterior angle of the stop sign. They do not ask for the angle sum, interior angle sum at all, so I'm going to go by the shorthand way that you saw before. Let's begin with the exterior angle measure, each of them. Let's divide 360 by 8. Remember, 360 is the exterior angle sum of any polygon. So that's 45 degrees. The interior angle of each guy is going to be supplementary to the exterior. So 180 minus 45 is 135 degrees. So those are those answers there. Again, I'm going to go the quickest route possible if they're not asking me for more information on those ones. Okay, last question, number 22. There are 3 parts. They say it has to do with 7.2 and 7.3. Maybe not literally at the same time, but just on a per part basis. In the diagram of the staircase shown, JKLM is a parallelogram. They mean right here. Hopefully you can kind of see me wrapping around that. JKLM is a parallelogram. QT is parallel. Oh, this is in the other staircase. QT is parallel to RS. QT and RS are both length of 9. QR is 3 feet. And measure of angle QRS, where is that? Is 123 degrees. All right, there's some information. Now, the other one also says a parallelogram. This is enough information for me to say, by the way, that this is a parallelogram. So let's see what information they go for. List all congruent sides and angles in parallelogram JKLM. Explain your reasoning. So it's all about opposite sides and angles that are congruent. So my reasoning will be those theorems. So segment JK is congruent to segment LM. Those are opposite sides. And we also have segment, which way should I go with this? I'll go downward. Segment JM is congruent to segment LK. Those are because of the opposite sides congruent theorem, I think is the name. Again, sorry if I botched the name, but that's what it is. The opposite sides are congruent. Angles. Angle J, I'm just going to call them just by those angles like that, even though they give more letters. Okay, angle J is congruent to its opposite angle L. And angle M is congruent to its opposite angle K. I know that angle L looks a little weird. I'm going to change that. Okay? Those are by the opposite angles congruent theorem. That's for that one part right there. That's part A. Part B. Which theorem could you use to show that QRST is a parallelogram? I was going to bring that up before. I can even copy and paste it from a different thing, but it was the opposite sides parallel and congruent theorem. So you do have QT parallel to RS and QT equal to RS. So opposite sides, congruent, and parallel theorem. I'm getting a little worse with copying problems over. I wouldn't necessarily copy over that whole statement there, but it's because the diagram is there for me that I think that it's just more, I'm not showing work on this from that to do anything. So sometimes I do. Find the length of ST, measure of angle QTS, TQR, and TSR. Explain your reasoning. So the length of ST, if you notice, ST is opposite that of QR, and we know that QR is 3. We also know this is a parallelogram. Opposite sides in a parallelogram are congruent. So it's equal to 3. This is, again, opposite sides congruent theorem. I'm going to say them out loud, if that's okay. Measure of angle QTS. I know I've been using single letters, but QTS, all the single letters. QTS is this guy right here. Now, we know 123 degrees from QRS. QRS, it's maybe hard to tell here, but QRS is opposite. These angles are opposite each other. This is the bottom right, and this is the top left, if you will, of that railway. So they're going to be the same. They're going to be equal in measure, right? They're going to have the same measure. So measure angle QRS is 123, so is this one. Opposite angles are congruent in a parallelogram. Measure of angle TQR. Where's TQR? TQR is basically this guy up here. I'm going to put a little double angle mark there because it shouldn't be congruent to this guy or this guy. should be supplementary to it. It should be a linear pair. Measure of angle TQR is 180 minus one of those measures. I'll just put 123. And that's 57 degrees. And then the measure of angle TSR should be opposite of that TQR, right? Measure of angle TSR equals the measure of angle TQR. It's opposite that, so same measures. That should also be 57 degrees. Being opposite that guy. There are a lot of other ways you could do that, obviously, because it has, it's also supplementary to one of those other, it forms a same side interior angle with the other 123s. All right, guys. Hey, look, that ought to do it for this little guy right here. This just went to number 22. It was a little 7.1 to 7.3 review, and it hit on a lot of the stuff that we did. There are obviously a lot more challenging questions that you could find within on the individual sections, and if you want to find them, go ahead and check them out in the description section down below. There's absolutely no way we're near done with Titanic. I don't even know if they're aboard the ship yet. Oh, it looks like it, of course. Did they just save Rose from the... I think so. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Take care. I will see you in the next one.